Okay, in this session we're going to talk a bit about areas in a plane and how we can use integrals to work that out. And it's very similar to dealing with area under a curve. And do a quick sketch, and this is similar to a sketch that's on page 394 of your textbook. Say I have two functions and I want to talk about the area between those functions. A, this is up to B. My upper curve, I'll say, is f of x. My lower one is g of x. For a setup like this, the shaded area would equal the integral from a to b of f of x dx minus the integral from a to b of g of x dx. At this point, when you're starting to talk about the area between two different functions, you're not really concerned about x-intercepts anymore because the positives and negatives end up balancing out when you do this. All you're really concerned about is which function is greater than the other. For an interval x in a to b, where f of x is greater than or equal to g of x, then the area bounded by x equals a, x equals b, f of x, and g of x, I should say y equals f of x, and y equals g of x, will be given by the integral from a to b of f of x dx minus the integral from a to b of g of x dx. And that's always going to work out so long as f of x is greater than g of x, which means occasionally you'll need to be concerned with any places where your lines may cross over with each other. So we'll just dive right in. We'll take a look at example 1 off of page 395, where we are asked to find the region, or find the area of the region. The region between y equals secant squared x and y equals sine x from x equals 0 to x equals pi over 4. Now my two functions, secant is a reciprocal trig function, so the lowest value we can take is 1, whereas sine is a trig function and its highest value is 1. So secant squared x is always going to be greater than or equal to sine x. So the area in question will simply be the difference between the integral from 0 to pi over 4 of secant squared x dx minus the integral from 0 to pi over 4 of sine x dx. Now, the antiderivative of secant squared is tangent, and the antiderivative of sine is negative cosine, which means, well, I'll leave it at that for now, negative cos x from 0 to pi over 4. Tangent of pi over 4 minus tan 0 minus negative cosine pi over 4 minus negative cosine of 0. A lot of negative signs buried in all this. Tangent of pi over 4 is 1. Tangent of 0 is 0. The cosine of pi over 4 is root 2 over 2, so this is negative root 2 over 2. And the cosine of 0 is 1, negative 1, which I'm subtracting, so I have plus 1. put all that together, I get a 1 minus a 1, and a 0 minus negative root 2 over 2, and I would just end up with root 2 over 2 as my area. So, nothing too complex at this point. Now, sometimes you might have to work out what the boundaries are yourself, as opposed to being given them. For instance, let's say that you've got my camera around a bit. Example 2 on page 395. And you're asked to find the area enclosed by y equals 2 minus x squared and y equals negative x. Not being given any x boundaries kind of implies that they must intersect someplace and give you an enclosed region. If you look at a graph quickly, and this is shown in the example as well, 2 minus x squared is an inverted parabola looking something like this, and y equals negative x, of course, looks like this. So that would be the region in question. So I need to find out where these two things intersect. And that's simply going to be where the two lines equal each other, or where x squared minus x minus 2 equals 0, and that happens at x minus 2 times x plus 1, or at x equals negative 1 and 2. So those end up being my two boundaries. This is at negative 1, this is at positive 2. The quadratic is always the greater function, so my area is going to be the space under the quadratic from negative 1 to 2, minus space under the linear function from negative 1 to 2. The antiderivative of 2 minus x squared would be 2x minus a third x cubed, evaluated between negative 1 and 2, minus the antiderivative of negative x would be negative a half x squared, integrated between negative 1 and 2. Thing in 2, I get 2 times 2 is 4, minus 8 thirds. Putting in negative 1, I get negative 2 plus a third. Here, putting in 2, I get negative 2. And putting in negative 1, I get negative half. Evaluating all that. 4 minus 8 thirds is 4 thirds. Negative 2 plus 1 third is negative 5 thirds, which is subtracting, so plus 5 thirds. Negative 2 plus a half is negative 3 halves. I end up with 9 thirds plus 3 halves, or 4 and a half, or 9 halves. Units squared. Now, sometimes your shape will be a little bit more complicated that you're interested in, and then you might need to break things up a bit. If I look at example 4 on page 396, I will show this more with the diagram they give than try to write it all out. Pardon me. You're being asked to find this shaded region. The upper line is y equals root x. The linear function is y equals x minus 2, which of course has x-intercept at 2. So in this case, I'm going to break this area up into two different regions. Call this region A and region B, just like your textbook does. Region A will have area from 0 to 2 root x dx, because it's just the area between the square root and the x-axis. Whereas region B in here is going to be integral from 0 to 2 root x dx minus, and I'm going to need to find what this intersection is. So where does root x equal x minus 2? That'd be where x equals x squared minus 4x plus 4, where 0 equals x squared minus 5x plus 4, or x minus 1 and x minus 4. X equals 1 is a very crude artifact. If I brought the line back here, I'd get an intersection at 1. So I don't really care about that. I'm interested at 4. So this should not have been the integral from 0 to 2. This should have been the integral from 2 up to 4. So that's where the intersection's happening. Minus the integral from 2 to 4 of x minus 2 dx. Alright, so I work these out. In this case, that is x to the 1/2, so its integral would be, its antiderivative would be x to the 3/2 times 2/3, evaluated between 0 and 2. The 0 is not going to contribute anything, so I get 2/3 times 2 to the 3/2, which would end up being 4 root 2 over 3. And over here, once again, the antiderivative of x to the 1/2 is 2/3 x to the 3/2, which I'd evaluate between 2 and 4. This, and the integral of x minus 2, its antiderivative will be 1/2 x squared minus 2x, evaluated between 2 and 4. Working that through, I put 4 in. Square root of 4 is 2, cubed is 8, times 2 would be 16 over 3. And when I put 2 in, I'm going to get that 4 root 2 over 3 again. Minus 4 root 2 over 3. Minus, if I put a 4 in here, 4 squared is 16, times half is 8. 8 minus 8 is 0. And I put the 2 in. 2 squared is 4. 4 times half is 2. 2 minus 4 is negative 2. Okay. There's not a whole lot of simplifying I can do in that yet, although I can combine the 16/3 plus the 2 to give me 22/3 minus 4 root 2 over 3. Something's gone a little off here. I'm trying to figure out what. That's x minus 2. I need to do the upper minus the lower, since I'm subtracting this. From 2 to 4. The antiderivative will be half x squared 2x, put 4 in, 16, half 16 is 8, 8 minus 8 is 0, 2 minus 4 is negative 2. Bear with me for one moment. Put that together like that, and that's fine. That minus that. Minus that. Which is what that would be. What that would be. no questioning is I get a different answer from the book, and an answer to be explained by that negative sign being different. But I don't see why that negative sign would be different. At any rate, total area of A plus B would be 4 root 2 over 3 plus 22 over 3 minus 4 root 2 over 3. These conveniently cancel out and leave me with 22 over 3. Well, I'm going to put a little asterisk by that because my answer is different than the book. I'm not entirely sure why, because it looks like our signs match up as much as I can tell. But if I'm subtracting a negative here, then I should certainly be adding. That's 4, that's the negative. 8, 16. Alright, that's it for now on that one. Now, the last thing that I will mention is that you can actually integrate over your dependent variable instead of your independent variable if it makes life easier. And I'm going to work off that. This is example 5, but it's dealing with the same area that was in example 4. So this is my setup. This is the area I'm interested in. And my two lines are y equals root x and y equals x minus 2. But I'm going to rewrite these slightly. I'm going to rewrite this as y plus 2 equals x and y squared equals x. What that lets me do in rearranging the dependency here, I can actually integrate over variable y instead of variable x. And in terms of taking the upper minus the lower, now I can start to talk about taking the leftmost away from the rightmost. And I can write the area equally as correctly as area between 0 and 2, because those are my y values in question, of y plus 2 dy minus the integral from 0 to 2 of y squared dy. Notice that the benefit of this is that I don't need to break the region up. I can just say that my area must work out to this. In the first case, the antiderivative is a half y squared plus 2y, evaluated between 0 and 2. In the second case, I end up with a third y cubed, evaluated between 0 and 2. 2 here, 2 squared is 4, times a half is 2, 2 plus 4 is 6. The 0 is not going to contribute. I get the 2 and I get 8 thirds. The 0 is not going to contribute. And 6 is 18 thirds. 18 thirds minus 8 thirds is 10 thirds units squared. Which should have been the same as I got in 4, but I made that error someplace that I couldn't find. This is the last I'm going to mention, and after this I'll go into, well, I'll just lead into this questions on the Google Classroom. I am going to take one more pass through example 4, because I want to see if I can find my error. So area A goes from 0 to 2 of this function minus that one, upper minus lower. Here I'm going from x values of 2 up to x values of 4. And I'm taking the upper function, I'm subtracting the lower function from that. Okay, that should be what I have. And that, in slightly different form, but matches up with what the textbook has. My antiderivative out front be 2 thirds x to the 3 halves. The 0 won't contribute to that. That would be 4 root 2 over 3. Coming over here, I get the same term here, evaluated between 4 and 2, minus a half x squared. Why are we adding here? Well, they just carried the negative sign through, which I haven't done yet, so that should be okay. At 4, this should be 16 thirds. And the 2 would give me another 4 root 2 over 3. Here the 4 squared is 16. A half 16 is 8. 8 minus 8 is 0. And the 2 squared is 4. Half 2. 2 minus 4 is negative 2. So this should be 0 from the 4. Minus negative 2. I dropped a sign. Minus negative 2. So this then becomes 10 thirds minus 4 root 2 over 3. So this is a 10 thirds. And this is a 10 thirds. And now we all match up. And I apologize for the confusion. If I wanted to write this out in a little bit more detail, I would say that this was a half of 4 squared minus 2 times 4 minus a half of 2 squared minus 2 times 2. And this all worked out to be 0 minus negative 2. Which is where my problem was there. Okay, that is all that I have to say about areas in the plane. There'll be some questions to go along with this in the Google Classroom. And thanks for watching.